Okay, good morning. So today's seminar, we're very happy that Han Wang is visiting from the University of Edinburgh. And in her very young research career, she has actually already, I think, worked on a very diverse set of topics. So she started out with a bachelor in atmospheric sciences from China, and then she moved to New York and did a PhD at the Courant Institute, working with Oliver Bühler. And her subject there was concerning with wave vortex decompositions. So she finished only in 2020. And then she moved to the University of Toronto for her first postdoc and was supervised there by Nicolas Grisoir. And after her first postdoc, she's now at her second postdoc at the University of Edinburgh, working with Jacques Van Nest and also Bill Young from Scripps. And today she is going to talk, I think, about what she did in her first postdoc, deep learning approach to extract internal tides scattered by geostrophic turbulence.
Thank you for introducing me and for having me here. And thank you for attending. So today I will talk about this work that started about 2 years ago from my previous job, and it's still continuing. The idea is to use a deep learning approach to handle a problem that cannot be done with classical methods. And this was done in the group of Nicolas Grisoir in Toronto before. I think I will use
my mistake.
Thank you. Now. Okay, good. So gentle reminder, what are the internal tides that we are trying to extract? They are internal waves generated from barotropic tides that are propagating over bottom topography in the ocean. And here, the barotropic tides refer to a somewhat boring kind of internal tides that are vertically uniform, and they are oscillating at the tidal frequencies in the ocean, and they are induced by the astronomical forces such as the moon and the sun. And the most energetic components of these tides are induced by the moon at the period of around 12 hours. And they are a very important signal for oceanographers because due to many reasons. For example, they can be part of the explanation for why the mixing is happening in the deep or upper ocean. And it can also affect people who want to infer balance flows from satellite observations. In that scenario, the internal tides are an important source of noise they want to get rid of. And they are also important for the detection of ocean temperature changes, which is in the field of oceanic tomography, where people try to detect the changes in the background stratification by detecting how the group speed of the internal tides of the internal waves are changing. And a more classical result, which is not at the frontier of the research anymore, is that a few decades ago, people were able to infer the loss of moon's angular momentum from tidal dissipation, and from that you can infer that how much the distance between the moon and the Earth is changing, and it seems to agree very well with theoretical predictions. And then so this is a very important source of signal, and the most popular way it has been extracted from satellite sea surface height observations is through this group of method called harmonic fitting. And it's the main idea is very simple. So suppose you are focused on a fixed spatial location, then you are regarding the sea surface height, which I will refer to as SSH from now on, as simply a harmonic series. So here, eta is what we denote as the sea surface height. Okay, great. So yeah, so we just regard eta as a Fourier series and here omega is the frequency corresponding to the tidal period, and this method works. So you are simply just fitting what you observe over this series and infer what is eta cosine, eta sine. And this method works even if the observations are causally sampled in time. For example, in the Topics Poseidon satellite observation, the observational period is about 10 days, which is much longer than 12 hours of the dominant tidal period. But the trick is to find some kind of least common multiplier between the two periods, between the period of the satellite observations and the tidal period. And then you just alias this period into a much longer period, which turns out in this case to be 62 hours. So when people analyze the M2 tide from the Tropics of Poseidon satellite campaign, they are basically fitting over this harmonic series over the omega that corresponds to 2 pi over 62 hours. And from this simple idea, people did manage to extract a lot of meaningful signals. And here is an example where a more complicated form of harmonic fit, but it's a little different, but it's the same idea. That's analyzed over 20 years of multiple satellite observations, and it's average over all the depths. And this is the M2 tide they found, and it definitely doesn't look like a noise. It's like a signal, and people can infer important properties about ocean mixing, for example, from these tidal signals.
And if you want us to see the pointer, you have to point at the. Yeah.
Okay, sorry.
I think so far it wasn't too complicated.
Okay, thanks for that. However, for this set of simple classical methods, there is a big problem, which is caused by what we call incoherent tides. In some other literature, this are also called non-stationary tides. They mean the same thing. They just mean that they are internal tides whose phase are shifting with time. So and this can really destroy the harmonic fitting in some cases. And here is an illustration about what I mean here. So suppose we have an internal tidal signal denoted by this blue line. So it has a fixed period, but you can see that it has some phase shifts around here. For example, there is a wider gap here than here. And then suppose this is a satellite that's passing through this time series, and it only has very coarse temporal sampling rates at these 3 dots, for example. Then if you apply the state-of-art tidal fitting method, you can only get this orange line, which misses a lot of the blue line. And the reason why you miss so much information is that there is a phase shift, and therefore you have no knowledge about the phase shift. So the most you can do is to construct a perfectly harmonic signal, which cannot possibly capture all the true signal behind. And these incoherence of the internal tides are very prevalent in the ocean. They are usually caused by various stratification in the background density or by nonlinear interactions with the balance flows. Okay, so let's go back to this picture I showed you before, where basically it's applying the state-of-art harmonic fitting to 20 years of satellite observation. And you can see a very strong signature of this pattern in the sense that there is a huge decrease of the internal tides around the equatorial Pacific regions. And this is log scale, so the decrease is pretty big. And there has been a lot of debate on what's causing this disappearance of these internal tidal signals around here. And some people think this is really reflecting some dynamical thing, like maybe due to some mechanisms, the internal tides are dissipated around these regions. But another possible explanation is that maybe there are actually a lot of internal tides here, but they are just simply not captured by the harmonic fitting. And this also makes sense because there are very strong balance flows around these regions. So the phase shifts due to the nonlinear interactions with the tides and the balance flows may be actually stronger around these regions. So therefore, there may be a lot of internal tidal signal, but they are just not captured by the harmonic fitting approaches due to these incoherent tides. And there is another, I think, a powerful demonstration about how bad the problem is. So these are results from a complicated ocean GCM, and it's called the HICOM model, and it's from a group in University of Michigan. And in the HICOM model, they have very refined outputs of like they have outputs that are very refined in time. I think they have hourly outputs. So if you fit over a harmonic series over all hourly outputs for a tidal period of 12 hours, you get a very exact true answer for how strong the actual tide should look like. And this is what they get from the true answer. So this is got from analyzing hourly outputs from the HICOM model, and this should be the truth of how strong the M2 tide is. And these three figures are plotting what you would get from harmonic fitting. I think so this one is applying the harmonic fitting method, and it's assuming that the satellites are passing at the rate of Topis Poseidon, for example. And this one is another like more refined kind of harmonic fitting, but it's also assuming that satellites are sampled at that rate. And this is also harmonic fitting, but this is based on space. And basically the main idea is that all these outputs from harmonic fitting methods fail to capture a lot of the raw signal here. And I think this is a powerful demonstration. And I also did a little bit of literature research on how bad this problem is in quantitative senses. And there is a popular metric people try to compute, which is the ratio between the looming square of the incoherent sea surface height tidal signals to the coherent tidal signals, to the sum of the coherent and incoherent tidal signals. And my general impression is that the newer the publication is, the worse this ratio gets to be. And like in 2017, this ratio is estimated to be 44% for mode 1. So it means that 44% of the tidal variances are not going to be captured by harmonic fitting. And also, and to make the problem even worse, it will probably get much worse for SWOT observations. The reason is that the SWOT observation is going to have much more refined spatial resolution, down to about 10 kilometers, which is about 10 factors more refined than previous satellite observations. And then intuitively at smaller scales, there should be more wave-main interactions. So the incoherence will be stronger at smaller spatial scales. And also the SWOT still have very coarse sampling rates in time. During the carval period, it has a sampling rate of 1 day, but during most of these observations, it will have a observational period of about 10 days. So it's still very coarse, and if you are doing harmonic fitting, you have to still do that aliasing thing, and then like it doesn't help that the signal is also strongly incoherent. However, for the SWOT campaign, there is opportunity provided for the internal tidal feeding method, which is that compared to previous satellite campaigns, which are essentially just track observations along one dimension, SWOT will have a very wide swath, which is around 120 kilometers. And so we can regard SWOT to be able to extract some kind of two-dimensional information as compared to previous campaigns. Therefore, the community is very excited by this, and we're wondering whether or not we can extract internal tides based on spatial information too, in addition to the harmonic fitting methods that are based on time. I'd like to summarize what I know about spatial constraint from the series I was aware of that can maybe help us extract internal tides. For example, statistically speaking, we know that internal tides concentrate around tidal wave numbers. So this can be seen if you just look at the dispersion relationship of the internal tides. And on the right-hand side is the square of the wave number. And on the right-hand side, omega corresponds to the frequency. And for a fixed tidal frequency, like M2 waves, omega is fixed, and F is the Coriolis frequency, and Cn is group speed that's related to the stratification. So it's related to the stratification profile, and you can get it from solving the Stern-Liouville problem. And here N refers to the vertical mode number of the wave. So yeah, there is that if you have a fixed frequency, then you and then if you also fix the vertical mode number, then the left-hand side is fixed. So therefore, therefore we should expect internal tides to concentrate around a certain tidal wave number corresponding to a certain tidal frequency. And this has been indeed observed from satellites too. For example, here you can see a bump here and another bump here, and they should roughly correspond to the first and second tidal wave numbers for the M2 tides. And another theoretical thing I know is that the low frequency components of of whatever you observe should be consistent with classical geostrophic turbulences. So here someone is plotting the energy flux inferred from sea surface height observations, and you can and this is looking at the balance flow, and then in the balance flow you can see that the direction of the energy cascade and entropy cascade indeed agree with classical turbulence series. So this is a constraint for internal tides because the geostrophic turbulence component is a major component in the sea surface height you observe. So this is saying that the remainder from the high frequency motion should obey some constraint, spatially speaking. And deterministically speaking, we again have the dispersion relationship I showed you before, and also if the regime is appropriate, then you may be able to you may also be able to apply ray tracing or tried resonance analysis to your data. And I think among all these spatial constraints I know, only the dispersion relationship and the consequence of the dispersion relationship has been applied to augment harmonic fitting. All the other ones have not been applied to augment these classical methods. And we are wondering with Nicholas in Toronto that since so much information is not used actually in fitting the tidal signals, maybe we can find some algorithm that uses that tries to make more use of the spatial information. And it will go one step bolder. We ask this very bold question on whether spatial information alone is enough to deterministically extract internal tides. So this was just an experiment we tried to do, but it turned out to be pretty successful. So the main idea of the project is to try to extract internal tides in a deterministic way, and we do that from a deep learning approach. And we do have observational data in mind, but we start with a very idealized simulation. In this simulation, it's just simulating a low mode internal tide that's excited around here, that's propagating through geostrophic turbulence induced by baroclinic instability. And here I'm showing one snapshot of the simulations we're using, where the left-hand side shows the total sea surface height, which includes all the frequencies. And so this includes the geostrophic turbulence and all the tidal components and all the other parts of the internal wave continuum. And on the right-hand side, we show this is presented the truth of the truth of the M2 tidal signal. So this truth is computed over very well sampled time series. I think it's maybe 15 minutes, and it's computed online. So since this is computed over a very refined time series of just on harmonic fitting, we can still get a very accurate estimate on how the tidal signals look like. And you can see that as the tide, the tides are propagating from here to here, and you can see that as it propagates through the geostrophic turbulence, you can see that in the beginning it was more coherent in the sense that they look more like plane waves, but as they propagate through the turbulence, they get scattered a lot, and the patterns are no longer plane wave-like. So then the main idea of the project is to train neural network to learn how to map from the raw sea surface height to the tidal imprint of the sea surface height. And the type of neural network we use is called the conditional generative adversarial network, or CGAN in this talk. And in a nutshell, a CGAN learns how to generate an image conditioned on an input image. So that's where the conditional and generative comes from in the name. And it composes of two neural network architectures. generator and a discriminator, and they are fighting against each other to co-evolve. So in general, the generator is trying to generate an image, and the discriminator is trying to discern whether an image is generated from the generator. The type of SIGAN we use is based on a popular algorithm called pix-to-pix. And this is an example from the paper introducing the pix-to-pix algorithm, where they are training the algorithm to learn how to map from a sketch of a building to a real photograph of the building. So during the training, it's fed with pairs of these building sketches and photographs, and it's learned, and then during the testing phase, this is an example they gave in the paper where this is the input image, and they ask the code to generate another photo, and this is what the code generates, and it compares well with the truth of the image. And so we are basically transforming this problem to our problem where we are asking the code to convert a raw sea surface height snapshot to a tidal sea surface height in fingerprints. And when doing this, we're treating the problem purely as a two-dimensional image translation problem, which is again motivated by the wide swaths of SWOT. And all the images during the training and testing are randomly shuffled in time, and there is no access to temporal information of the network at all. So this is the exact extreme of the harmonic fitting method. The harmonic fitting method uses temporal information and doesn't use much of the spatial information. And we are trying to use as much as spatial information as possible, but we didn't use any temporal information. And I think I ran out of time, so I will skip this introduction in deep learning.
I think we have enough time if you want to show them.
Okay. Okay, so just a very quick introduction. So both the generator and discriminator we have a convolutional neural network. This may be a little boring if you're already familiar with this. So by a convolution in the convolutional network, we mean that we train a kernel with like, for example, that looks like this with 9 coefficients. And then this is maybe how they look like from the initialization. And then we apply the kernel over an image, and it's just computing a dot product with the kernel and each of these patches. And the output is the dot product with the kernel and these patches as this is moving. And then during the training, we'll update the kernel because we want the output to behave in a certain way. And then there's also another kind of convolution, which is upsampling, which is generating from a smaller image to a larger image. And it's also essentially doing some kind of dot product where you dot product the kernel with this. Yeah, so you dot product this value with the kernel, and then you dot product this value with the kernel, and then you end up with a larger image. And after either this kind of convolutions, there is always a nonlinear activation function applied to the output, and it may look like this. This is what our algorithm uses. And this kind of nonlinear activation will introduce nonlinearity in the algorithm, which is very crucial for the network to succeed. And it's also a very important difference between neural networks and other database approaches, such as eigenfunction methods, because a lot of the other methods are purely linear, but a neural network is in principle able to handle nonlinearity in the data. Okay, I think I will skip. So the main idea of a SIGAN again is that it has a generator which generates from an input image to an output image, and it first does some downsampling convolutions and then does some upsampling convolutions, and it also has skip connections. This is a classic UNet network for the generators, and the discriminator. Discriminator is just something that keeps downsampling, and it just returns true or false. And in this case, it's trying to tell if an image is from the training data set directly or if it's generated by the generator. So these two networks are fighting against each other, because if the generator is very good at generating a fake image, then it would fool the discriminator. So then the discriminator would have a bigger loss function, and vice versa. If the discriminator is too good at this, then it will tell the generator that you didn't do very well, and the generator will try to improve from an increased loss function for the generator itself. So I think that the main idea is just that this is a very complicated neural network that are training two different architectures simultaneously. We have all idealized outputs of sea surface heights at 5 different turbulence levels. And here I'm plotting, here on the upper panel, I'm plotting the relative volticity in the balance flow. Yes, in the balance flow, and I'm numbering the turbulence level from S1 to S5, and S1 corresponds to a lower turbulence level, and S5 corresponds to a more active turbulence. And the lower panel is showing the corresponding internal tidal fingerprints, and we can see that as the turbulence level increase, the tidal signals also look much less like plane waves, and like they are scattered more everywhere. And we are dividing our training and testing data based on different turbulence levels. For example, in what we refer to as the ES1 run, we train the data from S2 to S5, and we test the data on S1. And we repeat this process for all the 5 turbulence levels. For example, in ES5, we are testing it on S5, but we train it on the lower turbulence levels. And we have, this is the best run we get from ES1 to ES5, and this one, the best run corresponds to the ES1 run, where again it's trained on the higher turbulence levels and tested on the lowest turbulence level, and we can see that so this is the truth of the internal tidal signal, and this is what our algorithm gives. This is the difference between the truth and the generated one, and this is the input to the algorithm. We can see that it's doing very well in almost all the measures. The difference is also very small in magnitude. And even though we randomly reshuffle the time during both the training and testing phase, it looks like it's almost reconstructing the temporal evolution of the tidal patterns too. It looks like so because it does so well at every single snapshot.
Han, can you say again how you get the truth?
Yes, the truth is so the model is run at a very refined temporal resolution, and the truth is computed through harmonic fitting of outputs that are sampled at every 15 minutes, and it's trying to fit a signal that has a period of 12 hours. So it has a lot of snapshots within each period, and it's just trying to fit over a sinusoidal signal.
So that's a traditional method.
Yes, it's a traditional method applied over very well sampled time series that are inaccessible to satellites.
And only one frequency.
Yes, yeah, because the model only forces the tides at one frequency.
Because you said there's always a spread.
Yeah. So the model also has sponge layers in here and here, so there isn't much trial thing going on. So there aren't much tidal periods at the 24 hours. And this has all been checked before. So that was our best run, but we also have worst runs, and our very worst run is the ES5 run, where we train it on the lower turbulence levels and test it on the highest turbulence level. I think it's still doing a reasonable job in the sense that it captures some statistical properties, like wavelengths is roughly matched, but it's definitely not as nice as the previous example because the difference is very big now, especially around the turbulent jet. And visually speaking, these two don't really match. And I think maybe I was okay. I will briefly talk about this. So to get some more insight on the behavior of these outcomes, we analyze the wave number spectra, and this is from ES4 run, which is our second worst run, but it's much better than the very worst run. So in this second worst run, we are comparing the wave number spectra computed from the truth and the generator. So here the solid lines denotes the wave number spectra of the tidal signals generated from the truth, and the dashed lines denote the ones generated from a neural network. And these two lines are the blue lines are computed over a different latitudinal band as the red lines. So that's why they look shifted, because the stratification profile are different in these two different latitudinal bands. So we think that the neural network is doing still pretty well in this room, because the location of these bumps, which correspond to the tidal wave numbers, are changing between different latitudinal bands, as we can see in the solid lines here. And we can see that the algorithm, the wave number spectra generated by the algorithm still captures the change of these tidal wave number bumps. So in summary, the algorithm is able to capture different spatial scales across the domain, even though the variation of the spatial scale is not by a huge factor. It's still able to capture them. And this is no longer the case in ES5 run. And this is just a reproduction of part of the figure in the ES4 run, where we can see that the two bumps overlap. And the ES5 run, there is a significant shift between the two bumps. And this is the ES5 run is the only run where we see such a shift in the tidal bumps. And we believe that this is a qualitative difference between the ES5 run and all the other runs. And here I'm just showing that if we compute some other statistical metrics, ES5 run is also much worse. And speculatively, we can think about why this is happening. And we believe the main cause why the ES5 run is behaving worse is because of the complexity. It's because of the complexity of the patterns as the turbulence levels increase. However, there is a possible fix to this problem, in the sense that we can see that ES4 run also have very complex patterns, but it's performing qualitatively better than ES5 run. So we believe that it's probably due to the fact that the ES4 run contains what we call overlay turbulent data during training, which is just saying that in the training data, we have the snapshots from S5 simulation, and S5 is at a higher turbulence level than S4. So it seems like if the algorithm have seen more complicated patterns during training, then it will do better during the testing phase. And so in principle, we can train another S6 run and feed it into training data if we want to improve the testing performance on the S5 snapshots. But this is more or less what we're already doing for ES4. So in summary, so this part of the work has been published on GRL, and there's a free version too, and the title is the same as my talk. In summary, we train a neural network to extract internal tides from idealized numerical simulation, and in contrast to harmonic treating methods, we don't need any temporal information, and it's acting on individual snapshots and try to extract the signals in a deterministic manner. And it's tested on turbulence levels that it hadn't seen during the training phase. And despite these challenges, it generates very good performances, both in terms of correlation factor, which I haven't talked about, and the tidal wave numbers. And the worst performance is at the ES5 run, but there is a possible fix by feeding the training data with over the turbulent data. And I want to spend maybe another 3 minutes talking about the current work in progress, which is motivated by the most frequently asked question when I present this work. Is the most frequently asked question is why we are using a conditional generative adversarial neural network for this task, because there are a million other deep learning architectures we could have tried. And a quick answer to this question previously was that if we use it on a simpler neural network, which is, for example, a UNet, which is simply a generator without a discriminator, then the performance is much worse than the SIGAN. So here is a snapshot from ES5, the most challenging run, and this is the truth of how the tides should look like. And this is from the SIGAN. It's not doing very well, but you can see that roughly the spatial scales are matching, at least in terms of magnitudes. But the UNet generates something that makes much less sense here. You can see it's very thin straps, which are not which is not even correct statistically speaking. And so again, this is from a much simpler neural network, which is simply a UNet generator, and it has much less parameters than the SIGAN. However, we went back to this recently because we met some experts in machine learning and ocean turbulence at UCLA, Kaushik, and he says we should try to tune our training parameters in the UNet and include this thing called learning rate annealing. So the main idea is that the way a neural network, network updates the parameters is through some kind of gradient descent, and for a gradient descent problem, you have a learning rate that controls how much you change in every iteration. And Kaushik says we should try changing this learning rate as a training process, and he proposes trying out this thing called cyclical annealing, which looks strange in this. So as the training proceeds, and here the horizontal axis is the epoch, which denotes how much the training has went on through the data. The learning rate is said to behave like this. It has a periodic behavior. It decreases first and then suddenly increases back and then decreases again. But if we try this more complicated form for the learning rate, we get a much better result with the UNet. So here, at least in terms of the statistical metrics, it's now comparable to the SIGAN now. Like it doesn't have these weird stripes anymore. And so this gets us very excited. So we're currently trying to get more work done based on this, because this network is much less costly in computation, and it's also easier to modify this to add some other physical constraint we like, for example, for this simpler neural network. So that's all I prepared.